Good morning to all of you in Vienna, and good afternoon, good evening, depending on which part of the world you're from. Today we have this side event organized by IIT Bombay in the Vienna Energy Forum. This is on towards zero carbon industry futures. And we are delighted to have an excellent panel here with us to discuss this issue. I'll quickly introduce the panelists. We have Bas van Ruben, who is at IIASA, and he is the leader for the Sustainable Systems Group at IIASA, and he's been looking at several of the scenarios and zero carbon scenarios, and he's going to set the context for us today. We have Professor Lars Nielsen, who's a professor of technology and in the Department of Technology and Society at Lund University. And we have Dr. Dorothy Krishammer, Dr. Dorothy Guban, who works at DLR, and she has been working on sustainable fuels. We also have, who will join the panel, Dr. Devashish Bhattacharjee, who is the Vice President of Tata Steel. So we are delighted to have a panel which has expertise in this domain and who will talk to us about this subject of looking at industry and looking at how industry can go towards zero carbon. So we'd like to request Bas to please set the context for us. What do you think in terms of zero carbon futures for the globe, for the world as a whole? Please go ahead.
Okay, thank you, Rangan, for this introduction. You should be seeing my my slides now. Yeah, I want to set the stage by looking at the role of the industry sector in rapid transformations to a net zero future. And so in the big picture, if in the Paris Agreement, we have agreed to limit warming to below 2 degrees, maybe to 1.5 degrees even. But if we want to limit warming to 1.5 degrees, we are already, to date, we are at about 1 degree. And the remaining carbon budget that we have until we exceed 1.5 degrees is between 400 and 600 gigatons CO2. And at the current rate of emissions, this means that basically in 10 to 15 years, at current rate, we would exceed that budget, and so that sort of sets the urgency of the issue in driving down emissions, so that we have more time before we exceed this budget. And in the scenario world, there are two perspectives on how to meet this target. The conventional approach has been that this 1.5 degree carbon budget is so tight that we probably need to overshoot it and then come back in temperature later in the century and go below zero with having negative emissions. But what we try to do in a study that we are publishing at the moment is to look at scenarios that do not overshoot and come back with negative emissions, but that have a rapid transformation towards net zero now, immediately at the beginning of the century, and then have net zero emissions globally afterwards. And so this big community effort that we are coordinating at the IIASA in the ENGAGE project explores the difference between the red arrows and the blue arrows here in this graph on the left. Red arrows are scenarios that overshoot and delay the transformation but then go negative later, and blue arrows are scenarios that immediately go down and don't go below zero later in the century. If you compare, these full century versus net zero scenarios, what we see is that for 1.5 or 2 degree scenarios, if you want to have the blue scenarios, the net zero scenarios, you need to reach global net zero much earlier than when you're allowed to compensate later in the century. And when we look what these scenarios would mean for the different sectors, starting from the present day situation, we see here the emissions in CO2 across the different sectors, forestation and land use and energy supply in green and red on the bottom, but then transport in light blue, and then we see the industry sector especially in yellow and dark blue towards the top, which are industrial processes and industrial energy use. And those are a considerable chunk of present day energy emissions. But if we look to their role into these net zero futures, we see that their emissions of industry are reduced, but often actually remaining still in a net zero world. And those positive emissions are being compensated by negative emissions, by carbon removals from the power sector and from land use. This is one illustrative pathway from one single model, but since we do this exercise with many different models, here you see on this top right graph the balance between positive and negative emissions in a net zero world across 9 different integrated assessment models that partake in our study. And you see that often the sectors below zero are the power sector and the land use sectors, the red and the green, and above zero, one still has in sectors like the industry sector, both processes in yellow and energy use in dark blue. Only exception is some of the models actually see sometimes the industry energy use or the industry processes being contributing to net carbon dioxide removals. If we look at the timing of net zero emissions, we also see then that land use and energy supply are the first ones to reach net zero, but industrial processes and energy use in buildings and transport and industry are much later, if reaching net zero at all. So that sort of is how across all of the integrated assessment models we see the emergence and the role of the industry sector in the bigger picture of reaching net zero, a net zero energy system in the second half of this century. And thank you. If you want to learn more about this work, go to our Engage Climate website or follow us on Engage Climate at Twitter. Thank you.
Thank you, Bas, for providing the overall perspective and showing us how industry is actually a relatively harder to abate sector, and also that the industry sector could go to net zero and also be negative. So I'm going to quickly show you a quick presentation in terms of the perspective on the zero carbon industry. And we start by looking at, if you look at the Kaya identity and you look at the total amount of CO2, we could typically break it up into the carbon per unit of energy, into energy per unit of materials, into materials per unit of the product, material intensity of the product, product per unit of service, into amount of services. So as we will, as the population wants to have larger amounts of services, we want to try and see if we can reduce the amount dematerialize, or we can reduce the energy intensity of the materials or the carbon intensity of the energy. And this immediately shows us the options that we have in industry. These options are energy efficiency. We can think in terms of benchmarking, whether it is cogeneration, process integration. We can look at resource efficiency. That means look at alternative raw materials that are less energy intensive or carbon intensive, dematerialization, redesign of products, substitution of materials, or we can look at having the same amount of energy, but we green the mix. We use solar photovoltaic, solar thermal, biomass, waste to energy. We can look at product efficiency and recycling so that less of the virgin material is being used. We can also think in terms of new generation processes. And finally, we can also think in terms of keeping the energy system the same, but capture the carbon and utilize it and then store it. So on all these options, there are actually several examples in industry, and I'm going to quickly take you through some of these examples and open up the panel then for discussion. So overall, when you look at an industrial process, we start from raw materials and we get the desired products. And in the process, we use a lot of utilities, but we can try to make this a cyclic process where we use most of the internal flows so that we use less of the external utilities. We had done in the global energy assessment sometime back, we had analyzed the entire industrial sector, and we found that though the industrial sector seems to be efficient when you compare it with each other, but if you look at it from a second law viewpoint, we can see that the efficiency is just about 30%, which means that the exergy efficiency of industrial processes is 30%. There are many, many processes which are possible, which can be more efficient in terms of use of resources. Uh, I'd just like to show you some sort of glimpse of some of the major industries and the Indian industrial context. So if you look at this, this shows that in Indian industry, in several of the industries, we are amongst the world's best. For instance, in the case of cement, of course, if you look at some of the others, we have some catching up to do when you compare to the world's best. And then there is, of course, the average. And so there are many industries which are much lower than the actual best practice within the country or globally. You can see a similar kind of emission. This is all these slides will be made available to you. This is the CO2 emissions, and interestingly, in the case of aluminium, though we were near the world's best, in the case of CO2 emissions, we are much worse than the world's best, and that is because the aluminium sector basically uses electricity, and a large amount of this electricity, it depends on the electricity mix. Most of the Indian electricity mix is from coal, and hence you can see the 18 tons per ton of aluminium, while the world's best is 3.3, where this is a plant which is using hydro for electricity. So there are many different options, and we can look at it. One set of options which is actually a no-brainer is in each of your industrial sectors, there are many different energy efficiency options, and these are usually cost effective in their own way. And then, for instance, in the aluminium sector, if you can change the copper you can look at replacing the steel with a copper collector bar, and in this industry we can see that this is it has a reasonable payback period. There are also new processes which are being talked of, and this is something which is in development. There's a new company which is focusing on zero carbon aluminium smelting, which is looking at inert anode aluminium smelting, and this is still in process and prototype, and the large plant is planned to be commercialized by 2024. This is process changes. Some examples in a textile industry in India, we're looking at solar thermal, biomass, and solar photovoltaic. And this actually meets all the requirements for the textile manufacturing in an Indian context. One of the examples from India. There are several examples of biomass gasifiers being used in steel re-rolling, aluminum melting instead of the fuel oil or the light diesel oil. And these are again things which are commercially applied in the small sector. This is a concentrator, solar concentrator, which is used in a dairy in the western in India. Instead of steam generation from the furnace oil, this is using with steam. We also have examples of carbon capture and utilization. This is an example from a fertilizer company where the flue gases are scrubbed, and you have a MEA system where you take out the CO2, and that CO2 is used in the production of urea, and you can see this is reasonably cost effective in terms of tons of CO2 saved. There are also processes which are now in the pilot scale where you integrate cement with calcium looping technology, so that the CO2 then is captured, and then that gets that goes out to storage. So several things are possible, whether it is related to energy efficiency, whether it is renewables, or it is related to carbon capture and storage. Now the questions which are there for discussion today in the panel is that, is zero carbon or low carbon an achievable goal for industry? What are the barriers? What are the policies needed to support these industry transitions? What needs to be done to catalyze the R&D required? Where will the investments come from? And is there a competitive advantage or disadvantage for industries that opt for low carbon? So with this, I will then open this up, and we will request our panelist. Lars, will you please go ahead and provide your opening remarks?
Yes, I also prepared a short presentation for you. And you see this now? So I would like to start where Professor Banerjee started with his Chi
We,
identity.
I don't see the slides. I don't know if others are seeing it. Can you try
Okay.
it again?
Okay.
Yeah.
Now,
Okay, we see it. Yeah, we see it. Please put it on slideshow. Yeah.
thank you. Starting where you started, Professor Banerjee, with your Chi identity and stressing the importance of looking at demand and materials efficiency and recycling for the purpose of having to produce less primary materials, primary production. I think a big change that has happened in the past years is that renewable electricity has become much less expensive with solar cells and wind energy technology. So electrification and hydrogen has become real and interesting options. And I think we saw a real shift in strategies in industry after the Paris Agreement, when it became quite clear.
Show up for us.
I have some sound there. Okay. So, for example, in 2016, the Swedish steel industry announced that they will become fossil-free. And just a month ago, they produced their first 100% hydrogen direct reduced iron here in May 2021. And they have also accelerated the plans to build a large-scale demonstration, 1.35 megatons per year, with a 500 megawatt electrolyzer capacity. So this is moving quite quickly now in the steel industry. It's not only in Sweden, but also in other countries. A lot of interest from car makers. So Volvo has hooked up with this hybrid project, but there's also been the announcement earlier in the spring of a high H2 green steel plant, a greenfield new steel mill where Mercedes-Benz takes an equity stake, and also a truck maker Scania gets involved in this H2 green steel. So certainly things moving quicker than one would have thought a few years ago. On the policy aspect that Professor Banerjee mentioned, we have done some thinking also around that. How can we think about this industrial decarbonization transition? And informed by different literatures, including innovation system literature, pointing to the importance of directionality. We need a clear direction for development for industry so that we're not creating new lock-ins, and we need to look at the whole value chain, not just the primary production. Of course, we need innovation and new technologies. Sorry. But even more, we need to think about how to create and reshape markets. How do we create green market demand? And as I exemplified, there is a demand, for example, for green steel in the car industry. We need to build capacity for governance and change also in the industrial sector. If you compare with the energy and transport sectors, where we have government ministries, we have government agencies, we have whole university departments working on transport and energy, we don't really have that when it comes to industrial transformation. And of course, industry is a tricky sector because we need international coordination and coherence because of competition between countries for industrial products, and also taking care of phase outs of, for example, blast furnaces and the retraining and reinvestments needed for making this transition. So that was a very short input to the discussion on policy approaches, and I hand back over to you now.
Thank you, Lars. Over to Dorothea. Can you tell us something about where you see solar coming in for the industrial applications?
Yeah, sure. Yes, so thank you for bringing up this topic for this panel today. I'm very happy to discuss about this zero carbon transition in the industry. If I would have to summarize it maybe in one sentence, I would say that the biggest challenge here, but also the biggest beauty of this transition is there's no one size fits all solution. So we heard from the previous speaker that probably the most prominent way and the most mature way we have been going so far is electrification. So we have available cheap electricity from renewable sources, and that's why we have to adopt our current industrial processes towards this direction. However, if we have a look at the global picture and the global industrial energy demand, what we find is that around two-thirds of the energy demand of the industry arises for thermal energy demand. And going even a bit deeper, of this two-thirds, around half of it is coming from industrial processes that demand high to very high temperatures, which means temperatures above 400 degrees C. And this could be a barrier when we look at electrification. And this is why concentrated solar power comes into the picture, I would say, and just in time for my slides, I would say. Um,
Yeah, you can tell me when to go ahead.
yes, so I just wanted to show you, show you a graph from a report of the International Energy Agency, and it shows that in the last 10 years, there was a huge increase on the installations of concentrated solar power plants, which is a very promising thing to see. However, what we also see is the starting numbers are extremely low. So even this increase, which means a very small number of installations, and even the EIA confirms that this shows a very large under exploitation of this technology, and we need more policy support to promote concentrated solar power. And next, I wanted to show you a couple of examples from DLR how we are able to integrate this solar thermal energy into different industrial processes. So my first example about the practical solutions partly by our institute is connected to the cement industry that we already saw some details about. And what I would like to show is that we managed to develop and demonstrate a solar rotary kiln that is suitable to be integrated in a solar tower that can provide the necessary high temperature for the solar calcination of the limestone. And then we release the concentrated CO2, which can be, of course, then captured by, for example, the chemical looping that was mentioned before. Another very important, also mentioned chemical for the industry is, of course, hydrogen. One example is, for example, the glass industry, where we need extremely high temperatures for the process, which is not even achievable, at least yet, with CSP technologies. That's why we need some sort of a fuel, which is hydrogen, for example, possible. Next example is the steel industry, where we need hydrogen for the reduction, also mentioned before. And I would also like to put here the ammonia industry, where one of the most important feedstock and one of the highest energy demand is coming from providing the hydrogen for the Haber-Bosch process. And here we developed two different concepts, one for the short term, let's say to reach the goals by 2050, and one on the long term. And the first concept is actually a hybrid electricity thermal plant which utilizes an electrolyzer. And on the long term, we are considering a fully thermal energy based process. so water splitting via a thermochemical cycle. And just to finish off, I would like to give some facts and figures about this technology. So currently we are able to reach around up to 1,000 degrees Celsius. Plants are available up to 200 megawatt. And what I would like to also put here, that one of the main barriers and one of the reasons for the low number of investments is the high investment costs, especially if we have a look at solutions with storage, which is, I would say, essential on the long term for continuous industrial processes. So here you can see the numbers. And this is why one of the main questions for the future is finding suitable storage solutions beyond the conventional molten salt, and probably sulfur is one of the most promising ones. Yep. Thank you very much.
Thank you, Dorothea. We now come to the last member of the panel. Last but not least, the most important is to get an industry perspective. So we are happy to have Dr. Debashish Bhattacharya, who's the Vice President of Tata Steel, joining us, and you can respond to the presentations made by the earlier panelists or provide your own views on the panel. Dr. Debashish, over to you.
Thank you, Dr. Professor Banerjee, and it was I listened to the others with great interest. So let me start by a view from the steel industry, and I'll try and share. I've just one slide, and I'll try and share that if that's possible.
Yes.
Can you see now?
Yeah, it's coming. Yes.
Yeah. Okay.
You can put it on slideshow, maybe.
Yeah, I'll try and do that as soon as I get to the next slide. There it is. So this is my only slide. And I'll just explain to you the problem and the approach that the steel industry in general takes, and the challenges thereof. So in essence, 1 million ton of crude steel produces about 2.5 million tons of carbon dioxide. And of course, around the world, we make about 1.8 billion tons of steel, not necessarily with the same route always, but the blast furnace route comprises about 50% or more of the, maybe 50 to 60% of the steel made around the world. So roughly 900 plus million tons of steel is made with a footprint of 2.5 tons of CO2 per ton of steel. So that's a lot of CO2. Imagine a country like India, where we currently make about 100 million tons and have the ambition of going to 300 million tons. We'll be making about 800 million tons of CO2 when we get to that ambition level, and that level we have to go to. But what are the ways by which we can contain the CO2? And as Dorothea said just a few minutes ago, and the others have alluded to, of course, one is CO2 capture. And then, of course, CO2 capture technology is slightly more mature thanks to many other industries. But at the hundreds of million ton level, perhaps it needs a little more investment, a little more scale up. But at about technology readiness level of 7 or 8, CO2 capture is possible through the amine route. But then what do we do with all this CO2? We just, not every geography is. By the way, can you hear me clearly?
Yes, yes.
Okay, thank you. Not every geography is amenable to sequestration. And most of the steel plants in India are located in geographies or in areas where sequestration is not a possibility, unlike, say, steel plants in northwestern Europe. So CO2 utilization is the only way. And the way to utilize CO2 is to fix the CO2 in a chemical compound, either organic or inorganic. So currently we have a pilot plant for CO2 capture in one of our steel mills, about 10 million ton capacity, and we can utilize the CO2 for demineralizing water, and only parts of that CO2. But that cannot address hundreds of million tons of CO2. So we need to produce organic compounds like methanol, ethanol, or even more long chain molecules, and even carbon nanotubes. So another way that we are trying to approach this utilization is to is to produce concrete by treating slag or concrete-like substance by treating steel-making slag with this CO2. But all these technologies for utilization of CO2 are at low technology readiness level, and utilization of large amounts of CO2 by any one of the technologies is far-fetched. So we see a view that if blast furnaces continue, then we need to upscale capture majorly. So that's a feasibility. But then utilization must take multiple routes in order to utilize all the CO2 that we will capture. And some of them will be methanol, some of them will go to ethanol, some long chain polymer molecules, and some even maybe to concrete, which will, utilization of blast furnace or in steel making slag. And of course, the utilization of CO2 to make methanol-like substance or organics will need hydrogen. So hydrogen in the steel industry has two purposes. One, of course, to replace carbon as a reductant, and the other is to utilize CO2 and to capture CO2 into an organic molecule. But then the challenge, of course, here is to generate cheap green hydrogen, which of course is something that we all want. And in geographies where electricity is green, and we have talked about multiple ways of generating green electricity, but it needs to go to the grid, it needs investment, it needs time. And in a country like India, where there is a national emphasis on green electricity, yet today it's only a minor percentage of grid electricity, and over the next decade and a half, we will get to about 50% or 50 to 60% of grid electricity nationally being green through solar or wind or combination thereof. So we need to find in the meantime routes to green hydrogen, cheap green hydrogen. And one of the ways we're looking at is, of course, biomass, which has a negative CO2 footprint, and negative in whichever way you look at it, of course, which means it eats away CO2 in the process of generating hydrogen. And chemical looping, has been alluded to in one of the talks before me. So we are looking at multiple of these ways to generate hydrogen. We are at this moment putting up a pilot plant for biomass-based hydrogen at one of our steel mills. And this hydrogen will be used in two places. One is to replace carbon in the blast furnace, and there is a limit to how much you can do that. And the other is to put it in gas-based direct reduced iron units, which are completely different non-blast furnace-based iron-making routes. And that brings us to electric arc-based steel making, which of course would wait for deep decarbonization till the grid electricity becomes completely green. So we see a future where, as long as the blast furnaces remain in steel making, we will need CO2 capture and utilization, and that adds cost to the tune that even up to about $200 per ton, and that will significantly offset utilization of steel in a developing country, and therefore development. And of course, the other is to generate hydrogen, partly to take care of the carbon, only partly to take care of the carbon in the blast furnace if they remain, and completely replace carbon in gas-based direct reduced iron route, which of course will need subsequently green electricity in the grid. So we see all this panning out over the next 15 to 20 years, with multiple routes being simultaneously used, green electricity being a fundamental need going forward, and multiple technologies for getting to cheap green hydrogen. Hydrogen has to come at less than $1 per kg to make it viable for the steel industry. So with this, I'll stop and ask for any comments and questions.
Thank you, Dr. Bhattacharjee. Can you stop sharing the screen?
Yes,
so
I'll
we'll be
just do
seeing
that.
Yeah,
I'll just do that.
So good. So we just heard from all our experts, and we are now opening up the panel to questions from the audience. We see that there are many of you have already asked questions, and several of our panelists have also responded. Let's be brief. Leonardo Barretto, would you like to ask one of your questions? Please unmute yourself and go ahead. You can ask your question to the entire panel. I think Leonardo Barretto is there. He's joined. Yes, please go ahead.
Okay, thank you. Can you hear me?
Yes.
Yes, the question was related to the presentation of Professor Nilsson. I just wanted to know what your take on carbon contracts for difference is in making green hydrogen competitive. Thank you. You think this is a good instrument for countries to levelize the cost of green hydrogen? Thank you very much.
The short answer to that is yes. We did look at ways of sort of supporting the early investments in the first hydrogen plants, and carbon contracts for difference seems like a very good instrument to achieve that.
Can I just request you to, just for the benefit of the audience, just explain what the carbon contract for difference is?
So yeah, it's in the European case, it's about guaranteeing sort of you guarantee a carbon price for, in this case, a steel mill. So if the market price for carbon emissions is lower than the price needed to make this technology competitive, the steel plant will be compensated for that difference.
Thank you.
Thank you for your answer.
Thank you, Leonardo. Alexander, do you have a question? Leonardo, I request you to switch off your video. Yeah.
I have a question to Tata Steel on what's the status on the Hisarna process. Are you working on that?
Yes. May I come in?
Yes, please go ahead.
So Hisarna, as you would know, it's 60,000 tons per annum pilot plant based in Amuiden in Netherlands. It has run 6 cycles of pilot tests. For about the last 1.5 years, it was hibernating in a way because of other policy and regulatory issues in Netherlands related to nitrogen, not related to carbon dioxide, as you may be aware. So now all that has been sorted out, and our next pilot trials have actually started, and we have run 20 to 25 successful days of pilot trials on the plant. Further trials are being planned, and simultaneously we are working on an upscale demonstration plant. We have not fully decided exactly where that plant is going to come up, but wherever it comes up, we need to start the design now, and is supporting pilot trials for the demo design will be conducted in the next 6 to 12 months. Does that answer your question?
Yes, it's very interesting.
Thank you.
Okay. From the audience, we have Ashwini Varnekar. Would you like to ask your question? Can you unmute yourself? Okay, we cannot manage. Okay, we have Nimal Valipuram. Please go ahead, ask your question.
You hear me?
Yes.
Hi, thank you. Yes, this is a question for almost all panelists. Anyone, if you can answer. I'm a bit confused about this in the whole Vienna Energy Forum. But when we talk about solar and wind being the cheapest, we also have to consider that the capacity factor of these plants. I mean, we are just comparing the nameplate capacity when we have solar and wind running at much lower capacity factor compared to coal, which is running at almost 90% capacity. I mean, are we considering these differences into our calculations?
Okay. Does anyone want to answer that question? Otherwise, I can also try. Lars?
Well, Nimal is absolutely right, of course, about the capacity factors, and you have to look at this as part of a system. The interesting thing with using hydrogen in industry, whether for steel or for ammonia fertilizer, is that you can have a fairly flexible production of hydrogen, and thus the electrolyzers become a big part of balancing the grid in the future.
Yeah. Just to add to that, what happens is that right now in the initial phase when renewables was relatively small, then even if we are looking at a capacity factor of 20%, when you look at the final cost of energy in terms of the amount per kilowatt hour, it turns out to be, it looks like it's cost effective. But as renewables gets to be more in the grid, there is a point where everything that you're getting through solar has to go through storage. And so then you have to add that cost of storage. But industry actually has a benefit, because if you are able to use hydrogen, you can actually use this, and you can use both with electrolyzers and fuel cells. You can use it also as a way to buffer and provide storage in the grid. So that could be interesting in that sense. Okay, thank you, Nimal, for your question.
Thank you very much. Thank you very much.
I request Anjana Das, would you like to answer? You've asked a number of questions. Would you like to ask one question to the panel? Would you unmute yourself? And
hello, everyone. Can you hear me?
Yes.
Okay. I wanted to ask that what about the water quality requirements in the green hydrogen production? Also, how do you think the countries with low water access can move towards adapting of green hydrogen technology?
Actually, I'm not an expert. I expect that you need a fairly high water quality for the electrolyzers. The idea, however, is that you take care of the water. So from the furnace, with the hydrogen reduction, water is generated. So the idea is to have a closed loop and not use new water all the time.
Okay, so it does not create a new requirement for extra water in the system.
No, the idea is that you have a closed system where you recirculate the water from the reduction step.
Thank you so much. I have one more question. May I ask?
go ahead quickly.
I saw in the presentation it's mentioned about the carbon capture. Can we use a carbon byproduct, the captured carbon, for the production of biochar?
So may I come in?
Yes, please, go ahead.
Yeah, so by capturing carbon dioxide, taking it to biochar would mean reducing the carbon dioxide itself, which is not what we would like to do. But if you're using a biomass route to produce hydrogen or syngas, then you get biochar, right? And that biochar can actually reduce the carbon footprint in a blast furnace or any carbon-based thermal or reduction system.
Okay, thank you so much.
Thank you. Okay, so let me, we are sort of going towards, we are running out of time. So let's ask to the panel a few overall questions in terms of the investments and the costs required for decarbonization, whether we look at hydrogen, whether you look at solar or renewables. Do you see this happening in the short term? What are the barriers? What do you see are the barriers, and how do we overcome them? So maybe we'll ask our industry expert first, Dr. Bhattacharya, and then followed by Professor Lars and the others if you want.
Thank you, Professor Banerjee. As I mentioned briefly in my presentation, any of the technologies that you put in to take care of CO2 will be expensive. If you use the carbon capture and utilization route, you're roughly adding 150 to $200 per ton. If you use a system like Hisarna, where carbon dioxide is the exit gas is rich with carbon dioxide, you can reduce that cost to about $80, $90 per ton, but still is additional cost. If you use hydrogen, unless, as I mentioned before, unless hydrogen is equal to less than $1 per kg and green, you're making steel unsustainable. Now, the whole effect of all of this is a huge amount. The capex needed for deep decarbonization going forward will be substantial. It will be almost on the same order of magnitude as the capex needed for an equivalent amount of steel capacity to be put in. Right. So roughly, you can work it out. 1 million ton of steel is $1 billion in capex. Yeah, so and any of the green technologies that you will put in, CCU, CCS, hydrogen generation through biomass or electricity.
So you don't see this happening at scale?
Well, it will happen at scale. It will need government intervention. It will need policy intervention. It will also mean that the commitments that were kept between the developed and developing countries that were promised to be kept, and so on and so forth. So the developing world will continue to grow in steel consumption, and it cannot afford to have steels at unreachable prices.
Right. Dorothea, would you like to add?
I agree.
Yeah,
I agree completely with our colleague from Tata. It makes producing basic materials more expensive. 20, 30, 40% for steel. It may double the cost of producing cement if you use CCS. If we look at petrochemicals, which is basically hydrocarbons using cheap fossil feedstock today, if you want to use hydrogen and carbon dioxide as feedstock, it becomes maybe 200% more expensive. So cost is the real problem here. So it means we need policy intervention to increase carbon prices and create markets and demand for more expensive but green materials.
Dorothea, do you have any suggestions on how we can get the costs down?
Yeah, I also agree with the previous speakers, but maybe I would like to add a new point in, which is public awareness. And there are certain industries where, for example, premium products could come into a question, let's say, especially fertilizer production, because yes, it will be always more expensive. So we have to find a way to make it worth for the customers. And I think the way to go towards premium green products could be a temporary solution at least.
Okay. So Bas, do you think that there could be changes and innovations on the demand side? That's what you were suggesting. And do you think this will also result in materials substituting other materials? So if, for instance, if steel or aluminum is very energy intensive and very carbon intensive, maybe we find other substitutes for them. Do you have any suggestions and ideas on this?
Yeah, no, that's what my research group is about finding how we can find alternative models to provide services. And I think we should, especially indeed if the cost of supplying these materials are going up, we should be creative in finding alternative materials for those products and minimizing the amount of steel or cement that you actually need. But I think you can broaden the scope and actually think about providing the services in a way that minimizes the material demand, right? So instead of having everybody aiming for their own vehicle and possessing their own vehicle, the service that we all care about is actually being transported from A to B. And if we can do so by car sharing, and the OECD, International Transport Forum, has made calculations that for a city like Lisbon, it's possible to provide all of the transport needs with about 3% of the cars that are currently in that city. And so even if we put some slack on that and say we can just reduce the number of cars that we need in order to provide all our transport needs with 10% of the vehicles that we have, just by having smart algorithms about who wants to go from A to B, we need much less material actually to provide that same service. And if then the cost of steel triple or double, if at the same time the amount of steel that you need to actually have the services that you want to consume goes down by 50 or 90%, that increase in the steel price is not that relevant anymore for the cost of the service. And I think that is another paradigm that we need to be really aware of and think more creative on not just thinking that the demand for materials is something that is set in stone. The way we consume is something we can change.
Is this something which will happen on its own, you think, in the market, or it will need some nudging to...
I think, yeah, that needs a lot of nudging. It needs public awareness of a different paradigm, right? It's another growth model almost that you need to bend away from what many people have in mind as the ideal consumer pattern for the future. But it is a model that can help us a lot in this coming through this climate transition.
Yes. So are there any comments on what Bas just now mentioned as a possible way in which we look at future decarbonization? Dr. Bhattacharya, do you have any? Yeah.
Yeah, sure. Thank you. And I agree with Bas. Reducing material consumption is the answer for civilization to go forward, I think. Not discounting the fact that we still have to decarbonize and spend the money to do so and find the money to do so. But the way forward for civilization is to consume less. Not that we reduce the quality of life, but answer the questions differently or ask different questions. How conveniently can we go from A to B? The components that we use in cars today can be lightweighted significantly if we design them differently. If we design them with multiple materials bonded together. So, you use steel where the stress patterns are demanding high strength. But where the stress patterns are not demanding high strength, you use polymers or polymer-based composites that will significantly reduce weight and reduce the CO2 emission. Yet you'll have a robust automotive vehicle. So just to give an example of how you can use multiple materials going forward and reduce consumption.
Okay, thank you. We're really running out of time. I'll just request each of the panelists to make a quick 1-minute last comment before we close the panel. So we'll start with Dr. Bhattacharya. Please go ahead.
So I think I'll repeat myself. Deep decarbonization will be expensive. We need to find the money. We need to find the policies framework to help industry decarbonize, and reducing materials consumption is the way forward.
Thank you, Dr. Dorothea.
Yes, maybe just to finish on a positive note, I saw some questions, comments about Africa. What I would like to say that also it's, I think, an opportunity for a just transition. And for example, we could involve these countries which have high, for example, solar energy availability, and bring the technology there, and then buy the product, for example, to Europe. And this could be beneficial globally as well for society. So it's not only a challenge, but also an opportunity.
Thank you. Professor Lars?
I think we should stop talking about industry as the hard to abate sector, because it's not that hard if you think about the technology options. Cost is a challenge, though.
Okay, Dr. Bas?
Yeah, actually, I agree with Lars here. I think we are in integrated assessment modeling work, related to his question, making a lot of progress at the moment with many projects expanding what's available for the sector and changing our view on what this sector could do in the context of the full transition. Okay. And we have to look very broad.
Okay, thank you. So we come to the end of this 1-hour discussion, and in an hour it is very difficult to figure out exactly how industry should go towards low carbon futures. But we've been fortunate to have a really knowledgeable panel and a very interesting discussion. I think in conclusion, we should say that there are a large number of options possible, and industry really may not be a hard to abate sector, but the challenge is basically going to be the cost. And this is where it needs both innovation, and it needs governments and industries to competing industries to collaborate and come together and look at creating new industrial futures which are more zero carbon. Thank you all, and we will share all the presentations that were made in this discussion. Thank you all for sparing time to be with us today.